Yeah.
Yeah, okay. So I'm very happy to have Professor Rajesh Prasad with us. He is well known, at least among the materials scientists, metallurgists in the country. He is also very well known among students for his videos and teaching material and teaching innovations. I had the fortune of learning about undergrad and master's teaching from him when I was his colleague for a very short while, though. So I'm very happy to have Rajesh, and
Unfortunately so.
unfortunately, so yes. So I'm very happy that so this has been something that we have been trying to do several times. We start a meeting, a seminar series, and then it gets stopped in the middle for some reason or other. So we are kickstarting it again, and Rajesh is our first speaker, and we have lined up several speakers both from India and abroad, and we have arranged it in such a way that there will be alternation between modeling, computational studies, and experiments. So we are very happy to have you with us, Rajesh. So you can start.
Thank you.
Yeah, please feel free to interrupt Rajesh anytime in between. So he's going to keep it very pedagogical and informal. So please make it more interactive. Yeah, sorry, Rajesh. Yeah, go ahead.
Yeah, so thank you, Guru Rajan, for a very nice introduction and also a very nice invitation to start this series and interact with the young and bright students of IIT Bombay. So I am very happy to give this talk. As you can see from the title, Anisotropic elastic properties of crystals. I have kept Young's modulus, Poisson ratio, and biaxial modulus. But while I was making the slides and saw that the lectures were growing larger and larger, and the number of slides was increasing. So I think if we can cover Young's modulus and Poisson ratio in this lecture, that will be quite good. And if time permits, we will do biaxial modulus as well. So the slide is not moving. So can you see my first slide now?
Yes, Rajesh, we can see.
Yeah. So this is a scene, this is a painting from Great Fire of London. So this was in 1666. For 5 days, 2nd September to 6th September, London was burning. The city of London virtually turned to ashes. Great monuments like St. Paul's Cathedral, what we see today, is not the one which was the original one. It was totally burned in 1666. So of course, this was a great devastation, and there was an equally great plan to reconstruct and rebuild London. And one of the major figures in that reconstruction and rebuilding was Robert Hooke. He was the architect and town planner of London after the Great Fire. We may not be knowing about Robert Hooke as an architect or town planner. He was also assistant of Robert Boyle at Oxford. We all know Boyle's law. It was Robert Hooke who made the equipment and made the apparatus to help Robert Boyle at Oxford. So Boyle's law has also Hooke's contribution. We know about Newton's law of gravitation. Here also, Robert Hooke had his claim. In fact, he had the claim that he was the one who initiated and informed Newton about the gravitation and the inverse square law. He was very close to that. Yeah. So he accused Newton of stealing his idea, and this led to a lot of acrimony between the two greats. Of course, Isaac Newton being more powerful suppressed Robert Hooke, but now there are historical evidence that Hooke also had something for his claim. He discovered cell biology. The word cell was first used by Robert Hooke in his famous bestseller, Micrographia. This is considered to be one of the first scientific bestseller. So he was Robert Hooke effectively was one of the first microscopists. And in 1665, 1 year before that fire, he had already written this book and established himself as a great microscopist. You can see the design and drawing of his optical microscope. And who was the one who drew this? Robert Hooke. He was an excellent artist. We are talking about a time before photography, before cameras. So everything which he was seeing through his microscope, he was drawing through his hand, by his hand, to show to the world. Here is the drawing of the flea. For the first time, mankind was seeing a flea in this detail. So both the science and the art of Robert Hooke was combining in his book Micrographia. This audience of metallurgists and microscopists may also be interested in crystallography, and Robert Hooke was one of the first crystallographers. In the same book Micrograph, this is a page from his book Micrographia, where he is showing these crystals as seen in his microscope. But he is also hypothesizing why these crystals have these nice regular shapes. So here you can see his hypothesis below. So he's thinking of some spherical building blocks which are repeating periodically to give different shapes. So he was conjecturing that all these are same material, same chemical composition, but why different shapes? Then he was showing that periodic arrangement of spheres can give different external shapes if arranged differently. So the atoms were not there in Hooke's time, but he was probably already thinking atomistically even at that time. Why are we interested in this talk about Robert Hooke? That was for an article he wrote 10 years after the fire in 1676, and that article is on helioscopes, telescopes to observe the sun. So he was interested in astronomy. He was interested to observe the sun's surface and its sunspots. And he was an excellent instrument designer. So he was describing how to make good helioscopes. And just like PhD students, when they write thesis, towards the end, they introduce a section called future work. Robert Hooke, in this article on helioscope, introduced a future work section and gave not one or two future work, a list of 10 items for future work. He was just a prolific worker. He was not able to contain himself in one field. In fact, some say that lesser recognition of him as compared to Newton or others, maybe because he distributed his energy into too many different fields. So a list of 10 items for future work. The third item is what is of our interest, the true story of elasticity or springiness. And what is the true story of elasticity or springiness as per Robert Hooke? This is it, yes. This is published word. This is not an English word. It is not French, German, Latin either. This is an anagram concocted by Robert Hooke, and he published it in that same paper, and he gave this as the true story. So it was a challenge to the reader that you decipher this anagram, then you will find what is the true story of elasticity. In 1676, for 2 years, this anagram remained undeciphered. Then, in 1678, finally, Robert Hooke, to his satisfaction, gave the final decipherment in a full article on spring. And he deciphered this anagram as at tensio sequis, as is tension, so the extension. That is what is Hooke's law as we now know today. Again, one of the drawings from his published work, again drawn by his own hand. You can see, when he is talking of F is equal to K delta L, he is not only talking of one kind of a spring, all kinds of a spring, helical spring, then a spiral spring like in the watches, and simple straight wire. Everything follows F is equal to K delta L. It's another story, and it will take us too far away from my topic. Is that why was he interested in springs? He was interested in a spring because he wanted to solve longitude problem, how to find longitude of a place. Now, how a spring is connected to a longitude is a subject of another topic, another talk. Now, this is how Hooke presented his law. F is equal to K delta X. Of course, probably he didn't even have the algebra or mathematics of this kind. So he presented it as is tension, so is extension. So F is proportional to delta X. Now we can write it like this. So this is Robert Hooke's law. Of course, in the modern terminology, this is presented differently because K of Hooke is both material and design dependent structural stiffness. It's not a material stiffness. So modern engineer need material property. For that, they had to wait another almost 150 years, 1678, because this concept of stress was not there. That came in 1822 with force being converted into stress by dividing by area, and elongation being converted to strain by dividing by the initial length. And then Hooke's law was couched as we now teach to students that stress is proportional to strain with proportionality constant Young's modulus. The beauty of this is that now the Young's modulus is a material property. The question can come to mind. This is a mystery that if sigma is equal to E epsilon is Hooke's law, then how the constant of that E is Young's modulus? That mystery is explained in the history of these 150 years, which took for this conversion. So this was a great engineering achievement to go from force displacement model to stress strain model. So we have our Hooke's law for uniaxial stress. There is a single stress and the strain is measured in the same direction as the stress. Although strain is measured in the same direction as the stress, it's not that the strain is uniaxial. So even for uniaxial stress, stress is only in the direction one, but strain is in both the direction, in all the three directions. Strain is in the direction one, the axial strain or longitudinal strain, and as well as 2 and 3, the transverse strains. The transverse strains are connected to longitudinal strain through a constant known as Poissons ratio. This is the negative of transverse strain by the longitudinal strain. If we put all these together, we can think of not just the uniaxial stress, but the triaxial stress. Uniaxial stress itself was giving triaxial strain. What the triaxial stress will give. So each component of the triaxial stress will then give their own longitudinal and transverse strain. So we know this, and by the principle of superposition, we can add the strains in a given direction. So the total strain in the direction one will be given by this formula, which is sum of the three strains caused by the three axial stresses. So similarly, we have epsilon 2 and epsilon 3. Is this the complete story? Not yet, because when we say triaxial stress, not only the axial stress, we have to talk about the shear stresses also. So not only there are three axial stresses, there are three shear stresses also. So the shear stresses are then related to the shear strains, and another constant is required to relate the shear stress to shear strain, that is the shear modulus. So if we now look at the complete picture, we have these 6 equations, 3 for axial strains and 3 for shear strains, and relating the strains to the stresses. The constants which are relating them, the E, nu, and G are called the elastic moduli or engineering moduli. And theory of elasticity shows that they are related by a relationship like G is equal to E by 2, 1 plus nu. So only two of these are really independent. If we know two of them, we can find other one. Let us now look at Young's modulus of copper. It is a CCP, cubic closed packed. That is, the unit cell is face-centered cubic. Copper atoms are sitting at the corners and face centers. Now, let us try to find the Young's modulus of copper. Well, we will not do an experiment on a unit cell. There will be several unit cells. So we are doing an experiment on a single crystal, but this is trying to show the loading direction. All of you material scientists know that along the axis, the direction is called, in the Miller indices, 001. And we load along 001. We find the strain along 001. So we will get the modulus along 001. But I can change the direction of the loading. Instead of loading along the axis of the cube, I can load it along the face diagonal of the cube. So now I am loading in the direction of the type 110, the face diagonal. Are the two moduli supposed to be the same? Well, copper, we know that copper has a given Young's modulus. We can search for it on the net and find out. So it should have the same Young's modulus in the two directions. But if you think about it, what is the Young's modulus coming from? Where is it coming from? It's coming from stretching of the bonds, atom to atom bond. And if you look carefully, along 001, the atoms are separated by a distance a, where a is the edge length of the cube or lattice parameter. But along 110 direction, along the face diagonal, they are separated only by a by root 2. So atom to atom separation in the direction of loading is different in the two directions. Why should the Young's modulus be the same in two directions? And it turns out that actually they are not same. Finally, you are stretching the copper-copper bond, and the forces between the atoms will depend upon the separation of the atoms. And if the separation of atoms are different, we expect the moduli to be different. And this actually is the case. So if one measures the Young's modulus along 001 direction, one gets 67 gigapascal. Whereas along 110, it's 130 gigapascal, almost a factor of 2. And if we consider the third direction, the body diagonal, it's still more, 191 gigapascal. Now it's almost 3 times the lowest value along 001. So Young's modulus is anisotropic. There are different Young's modulus in different directions. So what happened to our previous conclusion that there are two moduli, two independent moduli, E and nu, Young's modulus and Poisson ratio. Now we are seeing that Young's modulus itself is 3 here. And why only 3? You can calculate Young's modulus in all the different directions and find that you get different values in different directions. So you get a surface of Young's modulus. The way this surface is drawn is that the radius vector from the center of this drawing to the surface, that radius vector is proportional to the Young's modulus in that direction. So you can see that Young's modulus for copper along the 111 direction, along the cube corner, this radius vector seems to be longer. So the Young's modulus is large along 111 direction, as we saw. Whereas Young's modulus along the face normal, 001 direction, there is a depression there. And so Young's modulus is very less. Now this is for copper. All material will not show the same kind of variation. So if we look at molybdenum, it has a different value. So you can see, sorry. Okay, the values are not shown, but it's more depressed. It's opposite of this. So what you see is the highest value along 111 now is actually the lowest value along 111 for molybdenum. It's stretched along the cube axis and depressed along the body diagonal. So just often there is a misconception that cubic crystal, because A equal B equal C, is isotropic. So that is not the case we saw in the previous slide. And hexagonal, where C is not equal to A, is anisotropic. So hexagonal one easily accepts as anisotropic. Cubic sometimes, so there is a little difficulty. But cubic also is anisotropic. So here is the example of zinc, and one can see again enormous anisotropy. Along C-axis, it is such a low modulus, 36 gigapascals only. And along the AB plane, in the basal plane, the modulus is 122 gigapascal. This is not always the case. So another hexagonal example, thallium, it has higher value along C-axis and much smaller value along the basal plane. So this time, the C-axis value is 3 times the value it has in the basal plane. And finally, something which is close to isotropy. So magnesium. So it has value, the C-axis and the basal plane values are not very different. Although they are still anisotropic, it's not a real sphere, but it is like that. So this is just showing that same thing in a little bit more detail in the section. Sometimes it is easier to see in 2 dimensions than this 3-dimensional surface. So one can see this is the basal plane value along the, you can think of this as a 1 to 0 direction, which is lying in the basal plane. So 122 gigapascal. It could have been any direction because it is actually symmetric. So any direction in the basal plane will give you the same value. So 100 direction will also give you 122 gigapascal, and the C-axis value is 36 gigapascal there. So the maximum value is neither along the basal plane nor along the C-axis. It's somewhere there at some arbitrary inclination. Not arbitrary, one can find the inclination at which you will get the maximum modulus. Now let us look at Poisson ratio. Young's modulus is defined by one axis, and that itself is becoming anisotropic as soon as we start thinking in terms of crystal. Here we have now Poisson ratio, which by definition itself requires 2 axes, the loading direction and the transverse direction. So here the anisotropy is even more complicated and more rich, you can say. So even if the loading direction is fixed, so in this case 0, 0, 1, but if I change the transverse direction, all transverse direction will not have the same Young's modulus. All directions will not contract by the same amount. So what is the Young's modulus along? Sorry, I made a mistake. Loading direction is not 0, 0, 1. Loading direction is 1 bar 1, 0, the black line. The loading direction is the black line, and there are 2 transverse directions, 0, 0, 1 and 1, 1, 0. So in the transverse direction 0, 0, 1, the Poisson ratio is 0.8 to 1. And along 1, 1, 0, it is not just equal to 0.8 to 1, it's not even having the same sign, it's negative. And its value is minus 0.133.
So Rajesh, there is a query in the chat window, not
Yeah.
directly related to this, but it's an interesting question. How much pressure in GPA can be applied practically on a material in order to study the mechanical properties of the material? What should be the range? This is the question from Bhakti Kshirsagar.
Okay. How much pressure?
So the question is how much pressure in GPA, because you are talking about GPA. To study the mechanical properties, how much pressure can be practically applied is the question. So if you want to answer now or later, but I thought I will just let you know that there is this
Okay,
question.
okay. It'd be nice to have the question, and shall I try to answer? See, suppose you are measuring Young's modulus, then how much stress you will have to apply also will depend upon the cross-section. Means how much force you have to apply has to depend upon the cross-sectional area of your material, because the machine will finally apply a force, and that force of course is related to the stress, and how much force stress you apply, it can come either from your elastic relation sigma is equal to E epsilon, or from the plastic relation, depending on whether you are going into elastic deformation or plastic deformation. So if you really want to go to plastic deformation, then you have to apply an yield stress. So your applied stress has to be equal to the yield stress, and that yield stress multiplied by the cross-sectional area will give you the force, the kind of force which you should be having available in your machine to do the testing. So similarly, using your test conditions, your sample geometry and all, it is possible to calculate. A general ballpark answer cannot be given, but based on the material, based on the loading conditions, and based on the geometry of your specimen, forces and stresses required for testing can be calculated. So is that a satisfactory answer? Or
Yeah, thanks, Rajesh. If there is more questions, we will come back later.
Yeah, and you keep, it's nice that you alerted me, and I'm not able to see the chat box.
No, I will read the chat box. And
Yeah, so
let
you
know.
can alert me whenever there is a chat box query.
Yeah, sure.
Okay, thank you. So the two values are very, very different, and different in magnitude, different in sign. So are there surprises here? Most students who have not heard of negative Poisson ratio will first express their surprise on the negative value, that how come Poisson ratio can be negative. Negative Poisson ratio means that if I am stretching a rod, then in the transverse direction also it is expanding instead of contracting. So that seems to be quite counterintuitive. So negative Poisson ratio can be one surprise. But the positive value nu shown here, 0.821, is also should be a surprise if one remembers the classical limits of the Poisson ratio. Poisson ratio should be between -1. Actually, the negative should not be a surprise. Classically, it is allowed to be up to -1. It's the positive value of 0.821 which should be a greater surprise, because it is crossing what is being shown as an upper bound here. So this negative Poisson ratio, as I told, should not be really a surprise. And here is an article written in 1998 in Nature that negative Poisson ratio as a common feature of cubic metals. Actually, it is common. The copper which I showed you is not so special in having that negative Poisson ratio. Most metals, 69% of the cubic elemental metals which these people studied showed they are auxetic. Auxetic means showing negative Poisson ratio along 110 direction, 1 bar 0 direction, when loaded along 110 direction. So that is the condition which we were showing you for copper. And about the limit, there is an article in Quarterly Journal of Mechanics and Applied Mathematics shown here in 2005. In 2005, T.C. Ting and Chen established that actually for anisotropic material, there is no bound. So there was nothing wrong happening with our copper Poisson ratio going 0.8, because it is an anisotropic material. This bound shown here is for isotropic assumption. If we assume the material to be isotropic, the Poisson ratio cannot go outside -1 to 0.5. If it is anisotropic, no bounds. It can be anything from -infinity to +infinity if you believe Ting and Chen.
But Rajesh, isn't it still surprising that it goes to infinity? Because if you look at Nye, all these bounds are sort of derived using some positive definiteness of matrix properties? Or is it because Poisson's ratio is a ratio of the from the tensor certain components and one of them becomes zero or something?
I totally agree with you, Guru, because I also don't have this faith that it can really go up to minus infinity to infinity. Maybe the bounds are not -1 and 0.5. Bounds are large and different. And maybe that bounds depend also on crystal symmetry. So different cubic crystals will have certain bound, and triclinic will have a different bound, and so on. I don't know. So this paper is just too mathematical for me. And although I'm sharing this as a reference, I means I don't claim to have understood and absorbed their arguments and comments. So I will not speak for them. Okay. But it will be nice. I will like to look, I'm also interested. So I will like to explore this issue with you.
Sure.
And look at this paper a little bit more carefully.
Professor Prasad, these bounds will imply a huge deviation from conservation of volume.
Yeah. Conservation of volume is only 0.5.
Yes. So going
plus
to
0.5.
is really, what kind of a volume implications on volume of the sample?
Yeah. So see, in elastic deformation, because also we are talking about elastic deformation. And in elastic deformation, the volume does change because we have a volume modulus also, that is the bulk modulus, change in volume by initial volume. So the volume constancy criterion usually all right for plastic deformation, but in elastic deformation, we can have volume change.
Yeah, that's okay. But when volume is conserved, you get 0.5. So if you go from minus infinity to plus infinity, the implications on volume are huge.
Yeah, volume is huge.
So some other, for example, material continuity might break. Maybe there is fracture or something.
Yes.
Maybe they are extending beyond the limit. Yeah, it's possible.
Yeah. And this, interpreting, I think probably they have not really stated it the way I am stating it, minus infinity to plus infinity. But having no bounds really means this, minus infinity to plus infinity. That's where my doubt is also there, that maybe some other, based on certain criterion which gives this bound in, as Guru was saying, that those positive definite nature of the stiffness tensor that gives these bounds in isotropic. Same criterion may not give bound for anisotropic. That may be the case, but there might be that some other additional criterion can be there, something which may put finally some bounds to this. Because I also I will not vouch for, I will not try to defend this minus infinity to plus infinity, at least with my current state of knowledge. But yes, what you are seeing, that this, what we can still see, that this bound is no more true. And that is coming out by copper having a value of 0.83 along 001 direction when loaded along 110 direction. So this is obvious that this bound which was found is really restricted to isotropic materials and will not apply to an isotropic material. This much we can say.
Yeah.
Whether it is totally unbounded, and whether we believe their mathematical analysis is something to be seen.
Yeah, Rajesh Abhi also has a comment. He says for an anisotropic material, it's not a good idea to talk about Poisson's ratio as if it is a single number. So
Yeah,
he's telling that.
but so we can see it's not a single number, so it will be some collection of numbers. It's not even a tensor, so we can't call it that way. But see, I can still define a direction, and I can still define a transverse direction.
That's
And the question, and for that pair of directions, I define a Poisson ratio.
right.
So I just can't say that copper has a Poisson ratio of minus 0.133. But I can definitely say, it's the correct statement to make, that loaded along 1 bar 0 direction, and the transverse strain measured along 110 direction, the Poisson ratio will be minus 0.133.
Yeah. And there is also this negative Poisson's ratio in systems that undergo twinning, right? I mean, because they simply measure it as the change in dimension in the transverse direction, even though twinning in that sense will be considered as a,
Those are experimental artifacts, because twinning means you are already going into plastic deformation.
Yeah, it's plastic, but
Yeah. So those are errors due to measurement, experimental measurement and interpretation. Here we are talking about not that, but actual inherent negative Poisson ratio. So the best experiments you can do, avoiding any errors of the kind of that kind of measurement errors of twinning or plastic deformation, you should see that the Poisson ratio is minus 0.133 for this pair of direction. So for pair means answering
Abhi also has another point. He says, end of the day, the limits on Poisson's ratio in one transverse direction will have to be obtained using convexity arguments for the energy, which I think is the same as the positive definiteness. Because when they run the positive definiteness arguments on the stress tensor, which is represented in the matrix form, that is for generic anisotropic this thing. So they don't make assumptions about the C11, C12, etc.
Okay,
So that is what he is also saying, that it is the same as positive definiteness.
Yeah. So, but
okay, so
can I?
Yeah, we can get back. I think we have stopped in the flow of the talk. Yeah.
No. Means a brainstorming thought is coming to me that whether because of the anisotropy, the bounds also will be anisotropic. That is, there can be some bound for loading along 110 direction and a different bound for loading along 001 direction.
Yeah, it's possible, because generally Poisson's ratio for cubic, if you take, it is given as a combination of C11, C12, C44 probably.
Yeah.
So I think that will, and you get conditions only on C11, C12, etc.
Yes.
And so using them, then you should get what is the bound, I think. Okay, so we'll continue. We'll come back to it if there is more comments, questions, etc. So,
my student Srikant may be listening to this. Srikant?
If he's there, probably.
Srikant, are you there? Can he unmute himself or?
Yeah, he can unmute himself. Yeah.
Srikant, you are listening to me?
Srikant Bhatna, is it?
No, just S. Srikant. Not there in the meeting?
Not with that name. So, yeah, Srikant is there. There is one Srikant. Yeah. And probably he's trying to talk also. So.
Hello.
Hello, Srikant.
Yes, sir. Yeah.
You are hearing our discussion on the bounds?
Yes.
You have any comments to add to it?
Yeah. So it definitely comes from the positive definiteness, and since Poisson's ratio is a ratio of two components, like so it is S13 divided by S11 or S33. So it's a ratio of 2. So if the denominator quantity is going close to 0, so that is where, and the numerator can also be a high value. So when that happens, you will see a very high value of the ratio.
Okay, so means you are saying that you are not finding minus infinity to plus infinity so surprising?
It just means that without violating the stability criteria,
Yes.
the numerator of the Poissons ratio can go to a very high value, or the denominator has to come very close to 0.
Mm-hmm.
So dividing by a value which is close to 0 is going to give you a high value for the ratio. Yeah, I will have to go through that paper more clearly. And the paper says that it is unbounded in all crystal systems.
Okay, so I think for the moment this is sufficient.
Yeah.
We can continue now.
Yeah, I think so.
Any more discussion in the chat?
Nothing more. I'll tell you if there is.
Okay. So anyway, it was good because this was a confusing element for me also. So it was nice to be interrupted here and have some discussion. So this is now showing the Poisson ratio in the transverse plane for a loading direction which is perpendicular to the plane shown. And in the transverse plane, the direction is 0, 0, 1 and bar 1, 1, 0. So the loading direction is obviously 1, 1, 0. And these are all cubic material. So 1, 1, 0 is along the face diagonal. So we are loading along the face diagonal and we are looking at not only these two directions, but all the directions. So we get the Poisson ratio curve. And the circle at the 0 shown here is a 0 Poisson ratio. So if it is negative Poisson ratio, the curve will enter this circle, the 0 circle, the reference circle. So it is going from minus 0.5 to minus 1. Up to that has been taken in this diagram. And outside it is going from 0 to 0.5 and so on. The positive value. So positive value outside, negative value inside, positive value shown in the blue curve. So for silicon, although it is anisotropic, but unlike copper, it is not showing any auxeticity anywhere. It's positive everywhere. So along this direction, along 110 direction, it is a small value, 0.06. And along 001 direction, it is a high value and is 0.36. So quite a significant factor, 6 times. 6 times it changes within that same plane for a given loading direction. If we look at copper, we have already done that. And we saw that along 110 direction, there was auxeticity. So the curve has gone inside that 0 curve. So it is now negative. So those part of the Poisson ratio values are negative. So in this angular domain, you will see negative Poisson ratio for this one. And if you see lithium, you see that again, even greater auxeticity, the angular range is also high and the negative value is also higher than copper. Now, it's fine that we are getting auxetic directions in the crystal, but there are special loading directions along which if you load, that the entire transverse plane becomes isotropic. So this is 001 in the cubic copper crystal. So if I load along this direction, then along whether I look at 100 direction or 110 direction, I always get a Poisson ratio value of 0.42. So the entire plane, the Poisson ratio is the same. So in general, for a given loading direction, the transverse plane is anisotropic, but there are a special direction in which they are isotropic. So this shows again for the same 3 material, the isotropic directions. And 2 directions have been identified, the 001 and the 111. And you can see that for both these directions, although for 110 loading direction, they showed anisotropy, shown in the previous slide. Now all of them show isotropic values within the plane. Isotropic values within the plane, but still you can see the anisotropy that if you go to other plane, the value changes. So for 001 direction, it was 0.28 for silicon, but for 111 direction, it becomes 0.18. Similarly, there is changes from 001 to 111 for all three materials. But within the plane, they are isotropic. So an interest came to explore that which directions are isotropic and which directions are anisotropic in terms of Poisson ratio. So it is found, and it is a well-established result in the literature, that planes with isotropic Poisson ratio are the ones which are normal to a threefold direction, a fourfold direction, or a sixfold direction. In any crystal, if there is a threefold axis, you could see that in the previous diagram. So 001 in the cubic crystal is often the fourfold in these cases. And 111 direction is always the threefold. So they are symmetry related directions. They are symmetry related directions which are becoming isotropic. And twofold also can become isotropic sometimes, but only in the case of cubic point groups 2, 3, and M3 bar. As you are familiar, there are 5 cubic point groups. Cubic symmetry does not mean one symmetry. Any of these 5 symmetries will be qualified as a cubic symmetry. And in the first row of 3 cubic symmetry, 4, 3, 2, 4 bar 3M, and M3 bar M, they have, all of them have fourfold axis. 2 of them have fourfold axis. One of them, the middle one, has 4 bar axis, but that is also a fourfold axis, the fourfold roto inverse. So they have fourfold axis and they are cubic. But the last 2, the lower 2, do not have fourfold axis. They are still cubic. So fourfold axis is not a characteristic requirement for cubic crystal. Some of the students are always confused about this point. So I am insisting that cubic crystal need not require to be having fourfold symmetry. So in 2, 3 and M3 bar, there is no fourfold symmetry. But all of them, if you see, have the threefold axis, 4 threefold axis, 4 threefold axis, sometimes 3 bar axis with this dot inside. So 3 bar axis or 3 axis along the body diagonal of the cube. When the twofold axis of the cube, so like in 2, 3, the twofold axis is exactly in the location where fourfold was there in other groups. So if that is along the edges, parallel to the edges of the cube, 001 direction or 100 direction. So if two folds are there along 100 or 001 directions, then it is possible for these directions also to have isotropic Poisson ratio perpendicular to their section. So if my loading direction is this twofold in 2, 3, if it is parallel to that any of the two folds in 2, 3, I'll get isotropic section. But in 4, 3, 2, if I select this twofold or this twofold or any of the twofold, they are now not parallel to the fourfold. Then for these two folds, I will not get isotropic planes. So that's why twofold has to have this qualification, the twofold only with cubic point groups, 2, 3 and M3. Other twofolds, monoclinic has a twofold. That will not be isotropic. But 2, 3 has a twofold is isotropic. So this was a symmetry relation to the isotropic directions. Poisson ratios are anisotropic. A given loading direction will give you an anisotropic transverse section, but under special directions, under these symmetry directions, they give you isotropic direction. This is where I have already introduced you. My student Srikant brought a surprise. He's, as you can see from this figure, he's a keen footballer. He took IIT Delhi to a great victory in, he captained IIT Delhi team to a victory in IIT Guwahati Inter-IIT, which was a few years ago. So he brought a surprise. And the surprise was, finally, it got published in this paper, Planes of Isotropic Poisson Ratio in an isotropic crystalline solid. And the surprise was this, that loading directions without symmetry can also have transverse planes with isotropic Poisson ratio. This was not known till Shrikant did his calculation. Everybody was believing that only symmetry related directions can have isotropic Poisson ratio. So let us look at the example. So here is indium. Indium is tetragonal, 4 by mm. So classical wisdom will say that only the 001 direction, the four-fold axis, will be isotropic. And here is Shrikant's calculation coming up with these arbitrary directions shown in red and blue. No symmetry, not even nice Miller indices to be isotropic. So what Shrikant did was to create a nice way of three-dimensional representation of this anisotropy of Poisson ratio in a surface. So the surface is designed in a way that wherever you see the depressions, they are highly anisotropic directions. And wherever you see the protrusions, protruding parts, the hillocks, they are tending towards isotropy. And the maximum protrusion is the isotropic directions. So you can see that this is for a tetragonal crystal and the four-fold axis is vertical. So in the four-fold axis direction, there is a protrusion. And that is an isotropic direction. That is the 001 direction. But there are 4 protrusions here also. And those directions are also isotropic directions. So those are the directions E, F, G, H. And then the other directions A, B, C, D are these kind of hillocks. Or, yeah. Yeah, probably. Means I'm getting worried about correlating the 3D to the 2D picture here in terms of label, but we will see. And you also see that since it is a four-fold axis of tetragonal crystal, so the top view shows a nice four-fold symmetry of this Poisson ratio surface. And here, the eight separate directions. So there were 4 blue directions. Because of the four-fold axis, any direction is getting repeated 4 times. So that's why the direction E gets repeated into E, F, G, H because of the four-fold axis. And the direction A, the red direction, is also repeated A, B, C, D, the four directions. So 4 plus 4, 8 directions in indium, giving you totally isotropic cross sections in Poisson ratio. This was amazing and what quite interesting on its own. And this was not expected or thought of before. For hexagonal, if we see, there is a 6-fold axis. Again, the classical wisdom will only tell that the symmetry axis 6-fold will be an isotropic section. But Shrikant found that axes tilted at 56.25 degree in zinc, 56.25 degree, this red circle in the stereogram, all directions along this red circle, shown here in this 3D diagram as the edge of this bowl. So all those directions are also isotropic. Of course, once Shrikant had the calculational machinery, he wanted to take his calculation to the limit, and the limit you can take in terms of symmetry is to explore a triclinic crystal. And an example of triclinic crystal he found was copper sulfate pentahydrate. This is CuSO4, 5H2O, copper sulfate, quite familiar material, not so strange, but very unfamiliar crystal structure, triclinic crystal structure. And you can see the shape of the Poisson ratio surface now is also quite arbitrary. It's not having any symmetry. And here also, so the classical wisdom will say that there is no directions which will show isotropy in this crystal. And here, Shrikant had 6 directions which come out to be isotropic. Of course, being the being a non-symmetry crystal, although it has a symmetry group point group 1 bar is there. So these axes are not distributed in terms of any rotational symmetry about X3, because X3 has no symmetry. Now, all this story which we constructed of 2 independent Young's modulus was for restricted to isotropic solids. When we are handling anisotropic solids of the kind of the example I showed you, Shrikant's calculation, then these 2 Young's modulus, two independent modulus will not work. How many elastic constants are there for anisotropic solids? So that is the question which comes to mind. You have already seen that the cubic crystal itself has different Young's modulus in different directions. So E itself will have several, means there will be not just one E. There are several E's, several G's, and several Nu's. So this way of working out independent elastic constant will not work for an isotropic solid. So we have to look at it a little bit more fundamentally as relation between stress and strain. And we know that both stress and strain are second rank tensors with 9 components each. So a general Hooke's law. The Hooke's law is stress proportional to strain. But now, since there are 9 stress components and 9 strain components, which stress component proportional to which strain? So a generalized Hooke's law gives that a given stress component is linearly related to all the 9 strain components. And the coefficients now, which are incarnation of Young's modulus E. In the uniaxial case, sigma was E epsilon. Now, in the anisotropic case, sigma 1, is C1111 E epsilon 11 plus C1112 E epsilon 12, and so on. So you require 9 elastic constants just to describe sigma 11. And similarly, you will require 9 elastic constants for all the 9 stresses. So 9 into 9, 81 elastic constants are there. So it's a 4th rank tensor. This is a horrible news for any experimentalist. And he can only pray. Even to measure elastic constant of one crystal, 81 measurements is just too much. And God hears his prayer and gives a boon that let the stress and strain tensors be symmetric. They are symmetric for different reasons. Stress is symmetric because of the equilibrium condition. Strain is symmetric because of its smallness. And both are symmetric means now only 6 independent components are required for both of them. So a nice notation by Watt gives that rather than now writing them in a tensor notation of with 2 suffixes, we can write them in 1 suffix in this cyclic manner. So
Rajesh?
Yeah.
More generically, the strain should be symmetric even if it is large strain, right? It is symmetric because of the compatibility conditions.
Okay. So
that you derive from a displacement, and there you can have 9 components, but you cannot open up spaces or have overlap, and that condition is what gives. So even I think in large strain
Large
will
strain
still be
also has
symmetric.
to be symmetric.
I think maybe
Okay.
Abhi or somebody can comment.
No, that is a good point. So because I said smallness because of the normal, not looking at the large strain altogether, but the way it is derived symmetric for elastic strain, small strains. So you say that it's a displacement gradient, and then the displacement gradient is separated into symmetric tensor and an antisymmetric tensor.
Yeah, you can show the antisymmetric part to be a rotation. So it
Yeah,
doesn't.
but only for a small rotation. Only for a small rotation, antisymmetric part is a rotation. That's why I was having a feeling that this method will work only for a small strain. But what you are saying is important. And because for large strain rotations, rotation matrix is not antisymmetric. We know that. So only for a small strain, rotation matrix is antisymmetric. So this is what gave me the feeling, but probably a wrong feeling. You have rightly pointed out. This is the that the symmetry comes from smallness. But,
Okay. So I'm not sure about this
Yes.
large strain rotation part, but I thought it is from the compatibility conditions, but we can check it out.
Yes.
Thanks. Sorry for that.
In the large deformation gradients, the other issue will be that now the tensors will not be added, but they will be multiplied. Because the two tensors, to combine two tensors, one has to multiply the matrices.
Yeah, but they will also redefine stresses, right? Multiplicative decomposition. Then correspondingly, you will also define your. You can have this decomposition both additive and multiplicative, right?
Okay. What I was thinking that the general tensor means if I'm combining one large deformation to another large deformation, I have to multiply. But only if those deformations are small, the multiplication reduces to addition.
I see.
Multiplication reduces to addition, and only if they are addition, then I can describe it as symmetric plus antisymmetric. And only for a small, the antisymmetric is rotation. This was the logic I was following, but there can be flaw in this logic somewhere. I agree with you, because as you have told that even the large strain tensors are symmetric. So the symmetry must be having a little deeper origin than simply the smallness, as I told. So thank you for correction. I will look at that, and I'll have more discussion with you also on this. So,
yes. Sorry for the interruption. So go ahead.
No, most welcome, Guru. Most welcome, because this is what is the educative experience. Otherwise, if I keep rattling off and not interrupted, so I'll also not.
So there is also another question in the chat from Professor Nayak. So he's saying that these are single crystal considerations. So how do they relate to polycrystalline solids is his question.
Yeah. That's another ball game, Professor Nayak. And we have also attempted that in our other paper, which means one can think of averages or some sort of average moduli. So averaging again is not easy. So one thinks of average under special conditions. So that gives the Watt average and the Reuss average and things like that. But means these considerations which I am showing strictly will work only for pure single crystal. This analysis is for polycrystalline material. One has to take the polycrystal averages. In which case, the polycrystal, if it is not textured, may behave isotropically. But again, if polycrystal is textured, the anisotropy will come. But then the anisotropy will be a function both of anisotropy of the crystal and the anisotropy of texture orientation. It will not be just this pure crystalline anisotropy. And in a totally random orientation of crystals in a polycrystal, the crystalline and isotropy will be totally washed out, and the material can be considered as isotropic, which is what usually is done. Is it okay?
Yeah, okay. You can continue. If there are more questions, I'll interrupt you.
Yeah, yeah. So this notation, the 2 index notation is the tensor notation, and the 1 index notation is the Voigt notation. Now, since we have reduced the stress from 9 to 6 and strain to 9 to 6, we only have 6 into 6 relation. So 6 stresses, each of them related to 6 strains. So we again use instead of 4 index tensor notation, 2 index Voigt notation. So C11 is the coefficient which relates strain 1 to stress 1, and so on. If we do this, then we are left with 6 into 6, 36 constants. This is a huge improvement from 81 to 36. But experimentalist is still not happy. 36 constants for one crystal. It is still not a good news. So, and we have already got used to generosity of God. So we again pray to reduce this, and God again listens to our plea and says, let the stiffness matrix be symmetric. So the stiffness matrix now becomes symmetric. The symmetry of a stiffness matrix now comes from existence of elastic strain energy. So that is again a different ball game. So it's not so obvious that C12 should become equal to C21, because we are actually doing a totally different experiment. So if it is hexagonal and 1 is in the basal plane and 2 is parallel to the C axis, then 1, 2 and 2, 1 are totally different experiment. That whether we are stressing along the basal plane and measuring the strain along the C axis, or whether we are stressing along the C axis and measuring the strain along the basal plane. And the equality of these two is not immediately obvious, but they are equal. So 21, this reduces 36, 6 by 6 matrix. If it is symmetric, then we have only 21 independent constant. And this is the best one can do for a given general anisotropic system. Let us take a tour. I'm very keen on that. Let us take a tour of the birthplace of this elastic constants. Is my video visible?
No, Rajesh, video is not visible.
Yeah, how to put it on?
So probably you have to
Previously,
share
I was
that.
able to do, yeah, but
Yeah.
that knob is not working.
So
Anyway,
it should be
so
complete screen
it's
share.
okay.
Yeah.
Yeah, my face is not that important probably. But I thought sometimes the enthusiasm or something should be seen through the face. And I'm quite enthusiastic about this story. So 21 stiffness constant. Let us take a tour to the birthplace of this 21 elastic constant. The birthplace is not Harvard or Oxford or MIT. The birthplace of this birthplace of 21 elastic constant is a small town in England, Sneinton, with a windmill, which is used or which was used for grinding wheat for baking bread. This is where the 21 elastic constant was born. George Green, 1793 to 1841. Short life. But he was son of a baker. So since his birth, he was in this living in and around this windmill. And he was working and helping his father. He didn't go to school. No formal schooling at all. Maybe for a year or so, he went to some church school. But after that, no schooling. Help your father with the windmill. And how did he help? So let us look at that story. Receive the delivery of grain from the fields continuously, because grains will be coming and he has to receive that. Adjust sails of the windmill constantly to the wind speed. These sails, for efficient use, has to be properly inclined to the wind direction. And that those days there was no remote control or no electronic devices. So it had to be done mechanically and manually. And our George Green was doing that. Avoid danger of fire in case of stones. Ran out of grain to grind. That's why I received delivery of grain from continuously connected to that. Heavy stones are grinding against each other. And if there is nothing to grind, they will grind against each other and spark and will cause fire. Replace or repair stones weighing over a ton every month. Hard work. And this is the hard routine he was following. Where did he find time? Nobody knows. Where did he find time to write papers like this? This is the paper where he established Green's theorem. And this is the paper where he established concept of potential. Concept of potential is so important in physics. George Green is the father of potential concept. Mathematical analysis to the theories of electricity and magnetism. Look at the publisher. No famous publisher, printed for the author, because he never sent it to Royal Society or proceedings of the Royal Society, because thinking that who will accept a paper from an uneducated person? No school, no college, no nothing. Self-study. All of us who blame our circumstances should take George Green as example. So he wrote this, and who were the customers of this essay? His friends and family members. He sold them for some small amount. They probably didn't understand the meaning of the mathematics they did. But that was not where 21 elastic constant came from. That came from another paper on the laws of reflection and refraction of light. Laws of reflection and refraction of light? What is elasticity doing there? Well, please remember that this is George Green's time in 19th century, and the wave theory of light was coming to be established, but the wave of the light was moving in vacuum, and in vacuum, something has to be there to carry the waves. That was the feeling there, and that's the ether concept you must be knowing. But then, if you try to see reflection and refraction of light through the ether idea, then you have to assume ether to be an elastic material. And that has to have elastic property. And that's why those who are interested in optics were also interested in elasticity. And here, George Green quote is given where he finally establishes 21 elastic constants. But it was not all that easy. There was a big controversy in the field of elasticity, in the field of science, in the field of mathematics of that time. 15 versus 21. George Green saying 15. Other greater scientists saying 15. Who were those greater scientists? Cauchy, Navier. Who can fight with them? Well-established names in mathematics and physics and mathematical physics. So well established that France honors them by placing their name on Eiffel Tower. France has this tradition to engrave the names of their great scientists on Eiffel Tower. So their names are engraved on Eiffel Tower. And here is our poor baker's son, George Green, writing his paper from bakery in his spare time, saying that it is not 15, but 21. The truth finally won, and now we know that there are 21 elastic constants. So 21 elastic constants are there for a general anisotropic medium. Let us look at what these elastic constants mean. So C11 will be relating the strain in one direction to stress in one direction. So it is like Young's modulus in direction 1. Similarly, C22 Young's modulus in direction 2 and 33 Young's modulus in direction 3. So these three constants are Young's modulus. These three moduli you can show is shear modulus because 4 represents 2, 3. So it relates a 2, 3 stress to 2, 3 strain. So these are shear moduli. These three constants relate to Poisson ratio, which we have calculated and shown you. And interestingly, now comes the real surprise of anisotropic systems, that there can be tension shear coupling. These constants need not be 0. For many cases, they are 0. If they are 0, there is no tension shear coupling. They are 0 for isotropic material. That's why there was no tension shear coupling. Tensile stresses were expressed in terms of tensile strain. Shear stresses were expressed in terms of shear strain. But if you have an anisotropic medium, a tensile stress can cause shear strain and vice versa. That depends upon these constants, any of these constants being non-zero. And finally, this smaller triangle is even more interesting. This is cross shear coupling. That is, I apply a shear in the x direction. Think of a z plane, think of a cube, and think of the horizontal z plane. And I am applying a shear stress on that z plane in the x direction. But strain is not happening in that x direction, strain is happening in the y direction. So I am trying to shear the cube in the x direction. The stress is in the x direction, the strain is in the y direction on the z plane, if these constants are non-zero. So all these possibilities are there. Only for isotropic crystals, these constants are 0, so we don't have tension shear coupling. Even for crystalline material, often like for cubic crystal, these constants are 0. So even if we consider an isotropic cubic crystal or an isotropic hexagonal crystal, these constants are still 0. It's for some tetragonal crystal and triclinic crystal that they start becoming non-zero. And if you do the experiment of the kind I suggested, you will get that surprise that you shear in the x direction, but the shearing happens in the y direction. So triclinic crystal with no symmetry requires 21 elastic constant. More symmetric constant, if you are lucky, if your crystal is symmetric, you will have lesser constant. In the limit of highest symmetry, that is the cubic crystal, you will have only 3 independent constants: C11, C12, and C44. Other constants are 0, and these constants shown in one color are all equal. So 3 independent constants. And you can see both the tension shear coupling and the cross shear coupling constants are 0. So there is no such issue with cubic crystal despite its anisotropy. Who will worry about triclinic crystal? Well, one of our great physicists, ESR Gopal. I showed you a result of Nishrikant for a triclinic copper sulfate pentahydrate. Where did he get the elastic constants from? From this paper by Krishnan, Radha, and Gopal in 1971. They finally, using ultrasonic pulse echo method, they measured all 21 elastic constants. It's amazing. So this is the paper now which I initially intended But as I told that after making my slides, I realized that it will be too much to cover. This is a more recent paper where Shrikant has discussed the biaxial modulus in fiber textured thin films. But now, given the constraint of time and space, we have to postpone it for some future discussion. This is where that polycrystalline averages also we discussed. Now, sorry, I will end with this. I will end with this nice question. Nice question because I don't have any answer. Some of you, I don't know whether in chat box somebody asked, why certain non-symmetric directions are isotropic, as seen in Srikant's calculation. Well, we don't know. We don't have any intuitive physical answer. We have the elastic constants, experimentally measured elastic constants, as published in the publication data, and we just do the simple tensor calculation for finding the Poisson ratio in different directions. For some directions, we find it isotropic. So it's purely calculational, but the physics behind that is not really understood or not really known. So I accept or I surrender my ignorance to this question. But then, rather surprisingly, just going back. Yeah, rather surprisingly, why certain symmetric directions are isotropic? Sorry for the typo, directions being repeated twice, but why certain symmetric directions isotropic? Like we showed for zinc, the Young's modulus surface is like this. That means in the basal plane, the Young's modulus is isotropic. But the basal plane, the normal to the basal plane is only a six-fold axis. So the symmetry of the basal plane should be like a six-fold axis. It could have been a hexagonal prism. It should have been a hexagon.
But Rajesh, this is not answered by the Neumann principle, is it? Because that should be only the minimum. It can be more than that.
Yeah, I don't accept, Guru, that Neumann's principle is an explanation. What does Neumann principle say? Neumann principle only records this observation that the property symmetry can be has to include the crystal symmetry. It can be more. But why more? I'm asking why more? Why Neumann's principle is true?
Okay.
Some more physical means give me some physics-based answer. It means I'm looking for that. Means we should discuss this. And that's why I have kept this as a last slide.
Yeah, because the rest of your results are also the same thing, right? I mean, we are taking an anisotropic system and we are finding that it can have isotropy.
Yes, a fourfold, even the symmetry direction, yeah.
But it doesn't still disobey that principle, that it's not going lower than that. It's always,
It doesn't obey. So Neumann's principle is very, very nice. And it means it says that these are not violating Neumann's principle. But I'm asking
why Neumann's principle?
Yeah, means I'm asking. Forget why Neumann's principle looks like challenging a great scientist or something. I'm simply asking that a fourfold axis. Let us go back.
Raj, there is also another question in the chat box.
Just a moment, Guru. Before you ask that question, let me look at that symmetry question, because this is very close to my heart, and since you are getting interested, I don't want to leave you. So yes. So if I load along fourfold axis, if I load along means if I change my direction, loading direction anywhere along the fourfold axis. No, not sorry, fourfold axis. In the cubic, fourfold is not symmetric. So I was making a mistake, but threefold, perpendicular to threefold. In cubic crystal, perpendicular to threefold, any direction you take, okay, will give you the same Young's modulus.
So that is not like the 1-1-1 plane, is it? That doesn't have the hexagonal kind of.
Yeah, the 111 plane. I'm talking of 111 plane.
So 111 will be like a hexagonal basal plane, right? And
Yeah.
hexagonal because the 120 degree for the given symmetries,
Yeah.
because there are only certain numbers which are non-zero, that you can prove that it is isotropic, right? Basal
You
plane
can,
should
yeah,
be.
you can calculate. Yeah, you can calculate, Guru. Prove means you can calculate using these tensors. Okay.
No, I'm saying that if you have a cubic crystal, then only C11, C12, C44 are allowed for you.
Yes.
Then you can go to a plane, and in that plane, if you do this rotation, you can show that there is an invariance.
Yeah, so that's the tensor. That's what I'm saying, Guru.
Hmm.
That is the tensor calculation. That is the tensor calculation. But now I am saying that, and the C11, C12 which you are using is again from the experimental measurement. Right. But what I am saying that if I look at those directions crystallographically, those directions are not identical. If I look at the geometrical arrangement of atoms around those directions are not identical. So if the geometrical final the property is coming from the atoms, and if the geometrical arrangement along two directions are not identical, so for example, in hexagonal, the geometrical arrangement will become identical only if I rotate the direction by 60 degrees, not if I rotate the direction by 10 degrees. If I rotate the direction by 10 degrees, I'm in some arbitrary direction, which is very different from my initial direction, unrotated direction. So 0 degree direction and 10 degree direction are highly different in terms of their atomic arrangement and in terms of their crystallography. But in terms of my property, they are exactly identical. Yes, I can use my tensor CIA matrix and all to calculate that and to get this, but means I don't understand. I don't understand this symmetry.
Rajesh.
Yeah.
This is Abhinandan here. Hi.
Hello, Abhi.
Yeah, hi.
How are you?
Your argument is not going to take you very far. If you are going to look for the physical reasoning for isotropy or lack thereof, is not going to take you very far.
Yeah.
It's the property of the fourth rank tensor. Irrespective, I mean, right now you are talking about the elastic modulus tensor, but any property which is described using this kind of symmetric fourth rank tensor with 21 things and so on, and if you apply crystal symmetry, you will find this to be the case. So
yes.
It is contained in the mathematical entity which is this fourth rank tensor.
Yeah.
To counter your sort of physics-based arguments, all I would suggest is you also know that second rank tensor properties are isotropic when you have threefold, fourfold, and sixfold.
Exactly.
Right?
Exactly.
So,
yeah.
Okay, there is an observation. I don't know whether this is a law or anything. There is an observation that if the symmetry is 2 more than the rank of the tensor, that is fourth rank tensor and then sixfold axes and so on, then there is you can expect isotropy. Similarly, I mean, second rank tensor and then fourfold axis will get you isotropy, but of course threefold also gets you isotropy. Okay, but minimum difference is 2. I will have to look for some reference for this. When I find it, I'll send it across to you.
Yeah.
So, but that is contained in the mathematics. I don't think you can pull physical arguments to justify any such thing.
No, I disagree with you, Abhi.
No, you can disagree. All I'm saying is that the answer is not in the physics.
No,
you go back to the crystal. You go back to the crystal for a second rank tensor. I mean, to use your own words, the atomic arrangement along 1, 1, 0 is different from atomic arrangement along 1, 0, 0.
Yeah.
Why should the second rank tensor property be the same?
That's what I'm asking.
I'm
asking.
No, that is contained in the mathematics of it.
No. Electrical conductivity is not mathematics. Electrical conductivity is electron flowing along certain directions. And when
Right.
electron is flowing along 100 direction and they are seeing a periodic potential spaced at A, and electron is flowing along 110 direction and seeing a periodic potential of A by root 2.
We
Means-
can we can
Why-
we can
why?
keep arguing this, but ultimately, I mean,
No, this
I
argument-
say it's
Hmm.
it is an example of the unreasonable, correctness of mathematics,
Yes, yes, yes.
applicability of mathematics to physical systems. Never mind. I think Eugene Wigner said that.
Yeah. So means what I am trying to look for, whether there is some intuitive way,
No.
means intuitive or physical way. And if it is
No.
not there, it really surprises me. It really surprises me.
I don't think you need to be surprised. We take many things for granted because they come from mathematics.
Okay.
So Rajesh, there is another question from Professor Naik in the chat box.
Yeah.
Is there a model to predict the natural draw ratio of single crystal metals from the 21 elastic constants? That is the question. And the natural draw ratio is within quotes. So.
Okay. So what is natural draw ratio?
I don't know, Professor.
When you draw a wire from a sample, the stress strain curve actually gives an inflection, and the ratio between the extension, the stress strain at that particular point defines the natural draw ratio. So if you keep on drawing a wire from, say, copper, it will assume a particular dimension, and below that it will not diminish. There is no necking.
Okay.
Further necking. So you will keep on drawing a wire of the definite dimension.
Mm-hmm.
Okay. So that is the natural draw ratio.
Mm-hmm.
So the wire doesn't break. You keep on really drawing the wire, and then you will get a definite diameter of that wire.
Okay. So I think, Professor Naik, that is again a problem of plasticity, because you are actually deforming the wire plastically. So these theory may not directly be applicable.
Well, you get really a pseudoplasticity followed by stress hardening there, strain hardening, and that inflection, the joint between the two, is the point where you start getting the natural draw. So I was just wondering, whether, because that is one of the property of practical value. So any of these considerations giving you a very finely defined properties of a single crystal, do they yield something useful like the draw ratio? My interest is really not in metals. I am more interested in the elastic properties of the surfactant films. But I am looking for models which are available probably in metallurgy.
Okay. Okay, I think I don't have an immediate answer to your question, but I think it's an interesting question.
Okay, thank you.
Yeah, Rajesh, can I ask you one more question?
Yeah, Abhi.
Yeah. So the specifics of Srikanth's calculation you did not present today. But my question is this. Is there any combination of cubic elastic constants you will, whether they have the four-fold axis or the two-fold axis? I mean, you showed two different rows. Three of them have four-fold axis, and 2 point groups have only a two-fold.
Yeah.
Okay. And you said the two-fold ones give rise to the possibility, right, of some two-fold direction, which gives you isotropic Poisson's ratio. Is that correct?
In the 2-3 and M3 bar.
Yeah.
Can you see my screen again?
Yeah, I see that. So I'm
in the 2-3 and M3 bar, the two folds are isotropic.
Yeah. So that is the question. Irrespective of what they do, irrespective of what the C11, C12, C44 values are.
Irrespective. They are not dependent on the value. Okay.
I find it a little surprising, Rajesh, because if you go through Nye, there is only one cubic form for elastic moduli for all point groups. And because the Poisson's ratio is something that you are getting out of this elasticity tensor,
Yeah.
I sort of find it a bit surprising. So,
Yeah, but I think, Abhi, that is because when you take Poisson's ratio, it is the ratio of two strains. So these moduli appear in different combinations for different combinations of directions, I think. That is why you are probably...
But there is only one form, Guru. So,
No,
I mean,
but that form probably is meant for the 100 pulling, because if you pull...
No. I'm talking about in the cubic ABC axis, in that coordinate system.
Right.
You get only one form for the elastic compliance modular, compliance tensor or the stiffness tensor.
That is true.
Okay,
but,
given that, since you are deriving all the Poisson's ratio from this compliance tensor, my question then is, how I find this very surprising.
No, Abhi, if you look at Rajesh's one crystal where it was positive and negative, it was copper. So it had the same C11, C12, C44. But Poisson's ratio definition depends on, let us say...
Poisson's ratio being isotropic.
Isotropic.
I'm specifically talking about that.
Yeah,
I find it very surprising because all five of them have exactly the same form.
Yeah.
Okay.
Yeah, that part I agree.
So I find this surprising. Maybe there is some deeper reasoning here. I'm referring to page 140 of NI.
No, I'm aware of that fact that cubic crystal have only one set of means all of them will have that C11, C12, and C44 in the same form.
Yeah.
Right. Yeah. So given that
doesn't depend upon the point group.
Yeah, since you are getting the isotropic Poisson's ratio from this tensor, I find it surprising that you get it only for these two and not the other three. Maybe there is a bit more to the...
No, you see, no, there is no problem there. See, there the tensor is only with respect to x1, x2, x3 axes, isn't it? And is not relating to what is the symmetry along those x1, x2, x3. And if you see in the cubic crystal, it is the fourfold, whether there is a fourfold or a twofold. It is still the x1, y1 and z1 axis. These two folds which qualify are the x, y, z axes of the crystal. Right. The other two folds are not qualifying like that. So that's why these two folds, since they are actually it's the same region, that why these two folds become a special. I think the discussion is that why these two folds are special and give isotropy, whereas the other two folds are not giving. Monoclinic two-fold is not giving, tetragonal two-fold is not giving, or in the cubic, these other two folds in the top row, they are not giving. So that is because these two folds are a special being along X, Y, and Z.
Okay, got it.
And the fourfold is also along X, Y, and Z.
Got it.
So Rajesh, these are sort of invariants that you derive from the given tensor, is it? If it is some other frame of reference, you rotate to that frame of reference and you start looking for invariants in that tensor. Is that
Yeah.
Nice.
No, say that again.
So are you looking for certain invariants of the given tensor? Are these properties in terms of isotropy, etc., are derived from those?
Yeah.
That will also tie down to what Abhi was telling, that if you have this symmetry and so many and the tensor property, then how many invariants you can make probably decides whether, if there is no more left, then you will become isotropic or something like that. You have no more degrees of freedom in that sense. Is that
sorry?
What is happening? So
no, I'm not able to.
So this second rank tensor and fourth rank. So Abhi was saying that the difference is 2, or so it will become isotropic.
No. What Abhi was saying, if I understood him correctly, that there are certain property tensor rank relations.
Right.
So, for example, second rank property will always be isotropic for a cubic crystal.
Yeah. If you look at the Knight derivation, that is shown by saying that it is true if it is only symmetric, but if it is symmetric, then it is represented as the surface of a particular type, which you can show ellipsoid for real systems because all three numbers are real.
Yeah.
Then the demand that ABC you don't distinguish makes it a sphere. So that means all other directions are also the same or something like that. That is the way we derive that property, that it has to be symmetric. So it's basically a sort of eigenvalue problem. You show that the three principal directions and they have the same principal values. And because the generic ellipsoid that you can think of with this is a sphere, and so it should be a sphere or something like that.
Okay.
Okay, I mean, Rajesh, the paper that you are referring to, that is not the fiber texture paper, right?
No, this is the previous one.
Okay, is it already cited in the fiber texture one? If so, then I will download it from there. But otherwise, if you can send it across, that would be nice. I have the fiber texture.
I will send it to you. I'll send you both the papers.
Yeah, I have the fiber texture one, but yeah.
Okay, I will send you the
single crystal one.
Yeah.
Okay, great. Thanks.
Okay. So I think the formal talk ended before 25 minutes ago, maybe. Okay. But only we have been talking. So if there are anybody else, students or any other participants who want to have a comment, discussion, question, please feel free to unmute yourself and say whatever you want to say. And if you have some difficulty, type it in the chat window. I will read it out for Rajesh.
Yeah, it will be nice to have questions from students. Till now, we have had discussions only among faculty members. But one student had asked, no? You said.
Yeah, there was a question about the mechanical properties, how much stress.
GPA question.
I think because Young's modulus are in GPA, the tendency is to think that you have to apply something at GPA level to measure. And the second thing, I mean, which of course you mentioned, is that most students, if you ask, okay, how are these measured, they will say stress strain test. They don't realize that this kind of ultrasound wave propagation is the way to measure these
elastic
different
constant.
moduli. Yeah.
Actually, elastic constant rarely measured by these mechanical tests.
Mechanical, yeah. So okay, there doesn't seem to be any more questions.
It's like your physics example, that definition and measurement. So, for example, current is charge per unit area. Sorry, charge per unit time. Passing a given cross section, but it is never measured by looking at the charge passing a given cross section. It's measured by the magnetic field of the current
that produces.
So I think again the definition of elastic moduli and all comes from mechanics, but measured again by mechanics only, by different experiments.
Yeah, but by mostly wave propagation.
Wave propagation. Yeah.
Okay, there doesn't seem to be any more questions. So if that is the case, can we formally close the session? We can continue talking. If somebody wants to continue, yeah, I'm going to keep the...
Srikanth, can you switch on your camera and talk?
Hello.
You can say hello to Guru and Abhi.
Just a second.
They are my Guru, so they are your super Guru.
Yes.
Hi, Srikanth.
Hi, Srikanth.
Hi.
Yeah, so
it has become completely circular now. Rajesh is my guru and Rajesh says I am his guru. Right. So we are
like since the seminar is over, I mean, we can continue with our informal discussion. Rajesh, the specific thing that I wanted to ask you is, I mean, how exactly is this calculation done? The identification of that direction perpendicular to which you get isotropic Poissons ratio.
Yeah.
Do you do this for a generic elasticity tensor with 21 components?
Yes. So that's
Is it
why
guaranteed?
that
Is it guaranteed that you will always get one?
yeah, that depend no, that depends upon your. It's not guaranteed.
Ah,
Depends upon the elastic constants also.
okay. So you are actually fixing.
Mhm.
I mean, you are by doing this, by demanding that it should be isotropic perpendicular to a particular direction.
Yes.
You are imposing certain conditions on the numbers that those 21 numbers must obey. Is that correct?
Yes, that's right. That's right.
All right. Okay.
Shrikant, if you
Yes,
are,
sir.
if you can make yourself
And-
audible, yeah, you
and
can throw
Indian,
some more light on it. Shrikant is a better person to throw light on this.
Sure. All right.
Yeah, so you were asking how it is calculated.
Right.
For the Poissons ratio, if you see, the definition is minus S13 prime divided by S33 prime.
Repeat that again.
It is in terms of the compliances, because the stiffness one gives a more complicated expression. So in terms of the compliances, it is if the loading direction is along the x3,
Okay.
and the transverse direction that we are considering, if it is the x1 direction, then
okay.
the definition of the Poissons ratio is minus S13 divided by S33.
Minus S13 divided by
S33.
Okay, let me note it down. Yeah, that's interesting. All right, so that's how you define it.
Yeah.
And then you're fixing the third direction, the
Yeah.
Z direction.
Yeah.
Now you are rotating it infinitesimally.
Yeah, I will actually rotate it with, yes, sir.
Yeah, some arbitrary angle, and then
Yeah.
you are imposing the same condition, and that will give you some condition on the numbers. Is that correct?
Yeah.
Some condition on the S's, the 21 different values of S. It will impose certain condition.
Yeah.
Typically, how many such conditions does it lead to? Just one or many?
There are many. So in a few cases, like the high symmetry planes,
No,
there will be no
go to the
conditions.
triclinic case. Go to the
Yeah.
triclinic case.
Okay.
Go to the triclinic case and you impose this condition. Okay, some arbitrary rotation about the third axis, Z axis.
Yeah.
You are saying that the Poisson's ratio in the two conditions must be the same.
Yeah.
And that will give you just one condition on the 21 S's, right?
There are, so to be more precise, like to explain more about
Your
what I
video-
have done.
Your
It's
video is very
flickering.
unstable,
Yeah, it's
Shrikant.
flickering. I
So
don't
maybe
know.
maybe you can switch off. Yeah, maybe
Yeah,
you can switch
You
off.
can switch off the video, yeah.
Right.
Yeah.
Now
Okay.
talk, yeah.
Okay. So what I've done exactly is, so like I said, there is S13 prime divided by S33 prime. Now, keeping the loading direction fixed, I can rotate the one direction within the transverse plane. And for the Poisson's ratio to remain invariant, S33 prime is a constant because we are not
Right.
changing the loading direction.
Right.
So we don't have to look at the denominator now. So what
Right.
is actually required is the constancy of the numerator, which is S13 prime.
Nice.
Okay, so if I'm rotating it by an angle psi,
Right.
I can write the tensor transformation equations
All right. Got
for
it.
a rotation of psi about the given loading direction.
Right.
Now, so that means so if I take the derivative with respect to this rotation, it should be 0 if it is constant. So that's what I've done. S13 prime is written out, and then I've taken the derivative, and that will give us for certain planes. So it depends on the plane as well as the direction, right?
Right.
So for certain planes, so we will get conditions on the planes where the derivative of the numerator becomes 0.
Okay.
And in certain cases, there will be no conditions on the compliances,
Okay.
but they'll automatically turn to 0. Those are the high symmetry planes.
Right. Right.
And some of them will be, some directions will be dependent on the compliances. Like the
Right.
zinc case that sir showed, it's an angle at 56 degree. And now if I take another HCP metal, it might be some other angle.
Okay.
So there it's a compliance dependent direction.
Okay.
But the common fact is that the 001 or the six-fold axis is going to be isotropic irrespective of the compliances.
That's correct. That's
Yes.
correct. Whereas the other one at 56 degrees that you mentioned.
Yeah.
So how do you look for that direction though?
Yeah. So now going
What
into
is your
the
search strategy for identifying the direction perpendicular to which you get isotropic Poissons ratio?
Yeah. So I just write out S13 prime as a function of three angles now. It's sort
Right.
of you will have a theta phi which
Okay.
defines the plane, and a
Okay.
psi which defines the rotation within the plane.
All right. All right.
Okay. So
And it always yields a solution. I mean, I'm still talking about the general case where you have 21 different
no.
moduli.
There are materials where there will be no solutions,
Okay.
and some of them will have one solution, others will have more than one.
Okay.
So
And
I have not.
you have
yeah.
mapped it all out?
So for specific cases, I've identified all the solutions,
Okay.
and up to so cubic is easy to work with, and cubic will only have these high symmetry directions.
Right.
So we are
Right.
able to prove that
Right.
we can show that there are no compliance dependent loading directions.
Right.
That it is isotropic, and tetragonal is also easy to work with. There
Right.
also I was able to derive expressions
Right.
for each of the loading directions which are isotropic,
Right.
and it is easily up. I hear some disturbance.
Well, it's not coming from my room.
Okay.
Not from
Yeah.
my room either.
It is from my room. So there is some alarm going on. Sorry.
Okay. Yeah.
If it is a fire alarm, you should not be in the room. Okay, Srikanth, go on.
Yeah, so exact means what do you say? Final closed form expressions I've been able to derive for cubic,
Okay.
tetragonal, hexagonal, orthorhombic, and what is the other one? Yeah, these five.
In
For
all these cases, you are guaranteed to get something or the other. Is that correct?
not always guaranteed. Some of them, in all these
So if you
cases,
go
we
to-
have the symmetry planes, right? So those are guaranteed. But the ones without
Orthorhombic.
orthorhombic, sorry, it doesn't have. Yeah, orthorhombic also.
Huh.
You can have orthorhombic materials with no isotropic loading directions.
But okay, but isotropic loading directions are the ones that are interesting, right? So how
Yeah.
do you get that?
It orthorhombic can also have. I have examples of orthorhombic materials which
So
show,
where you say that, I mean, you impose certain conditions. If those conditions are obeyed by
Yeah.
the moduli, then you are
Right.
guaranteed. Okay, all right.
Right.
So you derive those conditions.
Yeah.
Lovely,
But beyond
lovely. So,
beyond orthorhombic, those huge ones, monoclinic, triclinic, and trigonal is also a bit complicated when it comes to calculation, because it has that S16 term non-zero, and S56 is also non-zero. So calculations are complicated.
right.
For those special cases, the equations have to be solved numerically.
Okay, all right.
So in that case, I don't know how many directions will be there or whether it will have solutions. We cannot say. Conditions I don't have, but the equation is there, which if solved by any method will give you the solutions. So
Okay,
the copper
all right.
sulfate that was shown in this presentation, that was those were obtained numerically.
Okay, okay, all right. So as the
And-
number of variables becomes larger and larger, then your method will have to depend on numerics.
Yeah.
And okay, all right, great.
Okay.
Nice work, Srikanth. So this
Thank
work is described in that paper, or you are still pursuing this some more?
Yeah, it's in the paper.
All these conditions on the elastic moduli.
Yeah.
that will get you this particular isotropic Poisson's ratio.
Yes.
Okay, great, nice.
The
I look forward to
equation is
receiving
there.
that paper.
Yeah, it's there in this presentation, slide 33.
No, Srikant, you send a copy to.
Yeah,
Ravi.
sure.
Yeah.
Okay.
Yeah.
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 Okay.
I was about to ask Shrikant, you have written your thesis?
No,
Not yet.
no.
Yeah. And that will have more details?
Yeah, I
Yeah.
will be giving more details there.
Yeah. So when it is
And-
ready, I would like to receive a copy of that also. Rajesh has
Yes.
already sent me these two papers, which I have with
Okay.
me. So,
Mhm.
uh,
Yeah, and I also have results for the shear modulus, which
Mhm.
I'm planning to write up.
Mhm.
So similar to
what is the
Poisson's
result?
ratio,
So what is the result, Shrikant?
there are isotropic planes for shear modulus as well.
Repeat that again. So,
So
within that plane,
any shear direction is taken, it will have the same value.
Same shear
Similar
model.
to for Poisson's ratio, we have a loading direction and
Right,
different
right.
transverse directions. For
Right,
shear
right, right.
modulus, we have a shear plane and different
Got it.
shear directions.
okay,
So
got it.
in shear modulus also, there are isotropic sections which have no symmetry.
Okay. So, and you have identified these things for cubic and tetragonal and so on. So you've
Yeah.
gone through exactly the same idea.
Yeah, exactly
Nice.
the same thing as for the
Okay.
Poisson's ratio, but different
Nice.
equations, obviously. Yeah.
Nice, nice.
Okay.
Great. Yeah.
Okay.
Thanks, Rajesh. So good to see you after a very long time. So,
Good to see you, Abhi, also.
yeah. Nice presentation.
All the travels are closed now, so very difficult to meet. Only meeting is
Totally.
through
Yeah.
online.
Totally. Yeah. That's true.
And online meeting also has proliferated so much now.
Right.
It's not easy to meet in online meeting also.
That's right. So at any given point in time, I mean, all of us have different meetings to attend. But thanks to Guru, I mean, we got a chance to meet. So this is
Yeah, it was. Thank you, Guru. I should thank him.
yeah, my pleasure.
It was a surprise opportunity. I was not expecting to.
So I
talk on this.
thought reading your paper, it will be easier for me if I listen to you first. So it was my own laziness which led to this.
no, that is also the reason why I showed up here. I mean, even though he sent me the other paper,
Right.
the fiber texture paper, I haven't read that yet. So, but I didn't realize that this talk is going to dwell on an earlier paper, which is nice. I mean,
And this fail. Yeah, sorry. You were saying
Go on.
something.
no, nothing. Yeah.
No, earlier paper you were saying something.
No. I mean, see, you sent us recently your fiber texture paper.
Yeah.
Whereas this particular talk is about an earlier work by Srikant, right?
Yes.
So, so I didn't come here expecting this work though, but now that I am aware of it, I just send me this paper and I'll be interested in going through it. So learn a little bit more about.
Guru also asked that biaxial modulus only to begin with. But I thought that let me discuss everything from the beginning. And from the beginning, when I started, I never reached the end.
Okay. Your abstract also talked about sort of doing some sort of homogenization for polycrystalline stuff. So, I mean, you're using a specific strategy for doing that, Srikant. Is that also part of your thesis, Srikant?
Yeah, that is also part of the
Okay.
work.
So, so what kind of homogenization strategy are you using? I mean, that's also numerical work, I suppose.
Yeah, it is also similar to this, mostly the tensor transformations again. So there also we calculate the polycrystalline averages for fiber textured films. And there are special cases where the Watt average coincides with the Reuss average.
Okay.
So that also was known to be occur only along planes with symmetry, 3, 4, and 6-fold. But then with further calculations, I was able to find that it can also coincide on planes without symmetry, or textures without symmetry. So that was one of the main findings. And
I had to pick up on this a little later. So there is an Amazon guy waiting outside. So I have to rush.
Another book for you.
No, this is something else. So yeah, thanks a lot. Thanks, Guru. Thanks, Rajesh. And thanks, Srikanth. I mean, this is really nice. Okay. See you guys.
Thank you, sir.
See you.
Okay. Bye-bye.
Bye. Bye.
Rajesh,
Srikanth, keep me in the mailing list for the future talks.
oh yeah, I'll do.
Hmm.
Professor Prabhu is also there. I don't know if he's waiting to say hi to you.
Hello, Nitya.
Hello, Rajesh. Hi.
Nitya.
Hi. Nice to see you. I'm actually simultaneously attending 2 meetings here, so that's the reason why. See, I've got so as you said, it's too many meetings going on, too many interviews going on. So fine. I mean, really nice. I enjoyed listening to your presentation, and also, I learned a lot from the work of your PhD student.
Thank you.
Yeah, sure. Thank you. Thanks a lot. Hope
Thank
to
you,
see you
Nitya.
soon in person. Yeah.
Yeah.
Okay, so if anybody else wants to continue, I'll keep the meeting. I think I can stop recording now, Rajesh. So I think all the interesting stuff is over now.
Okay.